Okay, let us now briefly talk about the different neural network architectures. And there's one note that I make down here. Note that BERT can both be seen as inducing those embeddings, or in other words, representations, and as coming equipped with a architecture already. So BERT, in a sense, is already representation and architecture in one go, so to speak. While before BERT, the natural language processing community were usually inventing different individual architectures, as I will outline now in the following. So the first architecture that I want to briefly discuss are convolutional neural networks, which also go by the abbreviation of CNNs. They were originally used in computer vision to extract salient features from an image, which allow classifying it. Yeah. So, for example, imagine you want to classify the image of a cat, and to identify the cat in an image, you would probably go by some very important features of a cat, for example, the ears or the nose. So these are the salient features. When you want to do such a classification, then one desirable property is translation invariance, which means that you want to recognize an object even when it is positionally displaced. To achieve this translation invariance, CNNs use a so-called weight sharing. So in the standard multilayer perceptron, each weight was independent and could independently be tuned. In contrast, CNNs have shared weights, so some weights are fixed, like they can take on a value, but it has to be the same value than another weight with which the sharing takes place. So two links in the weight matrix have to be identical, or several links, right? So this is there's always specific links that have to be identical, and those specific links, those specific weights, they also go by the name of filter. So you have one filter consisting of several weights, and this one filter may be responsible for different salient features. For example, one filter may be responsible for the ears, and another filter may be responsible for the nose, and then you use those filter to check whether your features are present or not. Yeah, so in contrast, the weights in an MLP are independent, and that comes with another drawback. So you would need a lot more data, because you have, if you, let's say you have 100 weights, so you have to train them individually. And as we've seen before, when we have a more complex architecture, we need more data. In contrast, CNNs, they have this sharing, so instead of 100 independent weights, they may only have 20 independent weights, so they can also work with less data. The translation invariance is pictured here also with the image of a cat, that no matter where it appears in the image, it's always a cat. So your architecture should be invariant to positional displacement. In NLP, we may also have this property sometimes when, for example, let's say an n-gram can be shifted around in different places of the sentence, such as this one outlined here, movie, really good. Okay, the second architecture, which is more important for the NLP community, are recurrent neural networks. So recurrent neural networks are ideal for modeling temporal data. So let's say you have data that comes in a temporal sequence. And what is a temporal sequence? Of course, also just an ordinary sentence is also a temporal sequence, because the words come in a predefined order, and the order actually makes sense. So when you classify a sentence, or you classify each element in the sentence, then that would also be considered as temporal. And of course, the same goes for spoken language, where the words appear in their natural order, namely the order in which you utter them. So we have temporal data, and we want to classify we want to classify a label at each time step, right? We don't want to classify the whole sequence, but each time step should get a classification. And oftentimes in NLP, this classification at each time steps depends on all of the previous history. So you have an infinite context, at least in principle. So with infinite, if you have a math background, that is a big concept, infinity. But what we mean actually, so there's no natural border that you can indicate. You cannot say it only matters to see the 5 previous words or the 6 previous words. So this context may be flexible, and that's what we refer to as infinite. So RNNs are standard workhorses in natural language processing because any text is a sequence of words or tokens, and many tasks are instances of sequential classification, such as part-of-speech tagging, named entity recognition, and many others. So how does the architecture look like? First, let's make a picture. So the picture is this one here, and this on the right is the equivalent picture. So we have inputs x, and they are time index t. So these are the different words. x1 is the first word, x2 is the second word, x3 is the third word, etc. Then we have here, so this is an illustration of a standard multi-layer perceptron. You have a matrix that connects to a hidden layer, which connects to an output layer. Now the difference between the standard model is that we have this recurrent connection. So actually, the output of the hidden state feeds back to itself. And why is this useful? This is useful when you unroll the recurrent neural network in time. So this is the time unrolled version, which is equivalent. And you see the direction of the arrows. So you start with x0, so that's your first word. You get the hidden state. So the initial hidden state doesn't refer to anything back because there was nothing previous to it. Then you make a classification. When you're at the first time step, again, you have your connecting matrix, and then you get your hidden state, but this hidden state is also informed by the previous hidden state, and then makes a classification, right? So you have also this connection from the previous hidden state. And you have this all along the model. Why is this useful? Let's say you want to make this decision whether can is a verb, like auxiliary verb, or whether it's a noun. Just from the word itself, you cannot decipher this, right? Because without context, you really don't know whether it's a verb or whether it's a noun. But now this hidden state is connected to the previous hidden state, which in turn is connected to the initial output. So once the model in this hidden state, it also receives a signal that, just like by traversing the arrows backwards, that the initial word was I. So it knows the previous word was a pronoun, so it's going to be much more likely that the second verb is not a noun, but it's actually a verb. And of course, if we're at a later time step, we have the knowledge about all the previous history, and in many cases, it's really good to have this infinite context, because the more context we have, the more potential for disambiguation. What the input token actually means. And if you like math, just sketch it here. So it looks similar to the multi-layer perceptron. So we have xt, the input at time t, multiplied by a matrix, and then we add to this the previous hidden state multiplied by another matrix. So we get a vector out here, then apply the non-linearity, we get our hidden state vector, then feed this in, so multiply this again with some matrix connecting between the hidden and the final layer, and then we often do a softmax because we want to do classification. And I said, like, softmax naturally goes together with classification, but note the difference is classification at each time step versus classification of the whole sequence. So then there are extensions. You cannot only look backwards, but you can also look forwards. So sometimes it's good to know not only the past, but also the future. You can do this in written language. When you see a word like rusty here, you know it's past, you know it's future. You don't always have this this desirable property. In spoken language, you do oftentimes not yet know the future because you can only hear the words uttered until the present time and prior to that, but not the words that will be uttered in the future. But when you have written language, you can use this. Then there's a special variant of RNNs, which are called long short-term memory networks. So they are much better, and they are the actual variant of RNNs which everybody uses. And the advantage of those LSTMs is, well, in RNN, in standard RNNs, as I've described them, what you can easily imagine is that the longer some information signal lies in the past, the more it gets forgotten, and it gets forgotten because you do those mathematical operations, you multiply. Well, first it has to go through this hidden state, then through this hidden state, then through this hidden state. You do those mathematical operations, and you can imagine that a little bit of the past is forgotten at each time step, right, that you have to go through. And those LSTMs can deal with this, and they address what is called the vanishing and exploding gradient problem, just to give you the names. Then we also have encoder-decoder neural nets. So, as I said, those are used for mapping an input to an output, and input and output can be of different length, and the order of the elements is also does not need to be the same in both of those sequences. And classically, encoder-decoder neural nets consist of two RNNs. So you take two RNNs and stack them together, and you can use them for machine translation. Let's take an illustration. So you have the first RNN, but without output, so you cut all the outputs because it's not making any output. What you actually do is, in the last hidden state of this first RNN, you represent all of the input, right? So you get the input, it feeds through, you get all the inputs, you make a global summary of your input in this hidden representation. Then you feed this in to the next RNN. So there is a next RNN, which then gets the representation, and upon this representation generates the output. So in a concrete example, this could be a German text, sie mag Katzen gerne, and you would want to translate it as she likes cats. Okay, let's go in a few recent developments. So one model class that has replaced the RNN and is used in the BERT architectures are transformers. So transformers, and they have replaced RNNs like since 2018 about. Transformers use the attention mechanism. What's the attention mechanism? So the attention mechanism means that, assume you do machine translation, you can use a global context to translate your input into an output, as we've just seen. So we had this global context here, but that's not unlikely to be an optimal solution, because when you translate a word, let's say here's a French text, you want to translate économique, right? So does it depend on a global context, or does it depend on a local context? Actually, it depends on a global and on very local context in input. Let's, for example, say the English word economic, right? And attention weights indicate to what a certain output attends to. So what does it actually pay attention to? So we would imagine, or we can easily intuitively imagine, that economic, as I said, should pay attention to just a very little local context. And this goes for all of the words in the output. They are generated by just looking at a little bit of input text rather than all of the input text, right? And this is a very natural assumption that there is something that pays attention in translation or in similar natural language processing tasks. So the transformer and this attention has really boosted those machine translation models that we've seen. So before attention, they worked only a little bit. After attention was introduced, they worked much, much better. Now transformers make heavily use of attention, right? And also they use something called self-attention. Additionally, they give up this recurrent connection and say, okay, let's not use a recurrent connection, but let's use actually attention and feed forward. architectures and combine them in a complex architecture, right? So it's actually a rather complex architecture that combines feed forward networks and attention. And it has been empirically shown that this works actually very, very well. And there's additional advantage because we don't have recurrence. We don't have to wait until the previous time step is computed. And instead, we can do everything in parallel. Because we can do everything in parallel, we can process much more data and we can train our model on much more data. And this is exactly what has happened in BERT. So BERT has been pre-trained on huge amounts of data. And this was, at the time, only possible using parallelization, right? So, this architecture is very well suited for the principles of BERT, namely leveraging huge amounts of data. Another cool thing that has been introduced a long time ago, and like even in 1993, and still intrigues researchers until now. So people have forgotten about it. They rediscovered it in, let's say, 2014, 2015, 2016, and that has really been intriguing. Is you don't only learn one task, but you learn multiple tasks jointly. So what learning one task means, you do like part of speech tagging or sentence classification. And while this is cool, it's not how humans learn. Usually, we learn multiple tasks jointly. So, for example, we learn, like babies, they learn to see and to name an object jointly. Or, for example, if you learn a language, such as French, it may be helpful for you to also know about Spanish. So, doing those things jointly really allows you to leverage knowledge from one task to the other. And this is the idea behind multitask learning. It's like a more human-like way of machine learning. Another cool things are generative adversarial networks. And here the idea is that you have two networks that are connected to each other, and they try to outsmart each other. So one of those networks goes by the metaphor of counterfeiter, which in Deutsch is Währungsfälscher, and the other network goes by the metaphor name of police. So what they're trying to do, the counterfeiters, the first network, they're trying to make fake data. So in computer vision, a fake data could be a fake image. So this is a famous example where you have celebrities, and the network has been trained on real celebrities and then generates fake celebrities. So these people here actually do not exist. They are generated by our neural network. So the first network tries to make fake data, and the second network, the police, tries to decide whether it's fake or whether it's not fake, whether it comes from the real data or whether the network has just hallucinated it. And then they iteratively try to improve each other. So the better police is at detecting that this currency is fake, the better do the counterfeiters have to get. So the counterfeiters make more and more effort to fake police into believing that this is a real image or a real object, and the adversary, and so that's the adversary, and the police tries to detect this. So they iteratively improve each other until they reach an equilibrium where the counterfeiters are so good that the police can only randomly guess. So actually what the counterfeiters produce is indistinguishable from the real data. And once you have trained this, you just use the counterfeiters to produce new data, right? So this is a cool idea. And then the second aspect of having an adversary, right? So the counterfeiters are the adversary. So they try to fool the police, right? So, and this aspect also has become very important in deep learning, like fooling the model, as we've seen before, with this adding of pixels to the image, so that the network then says pig, right? So it completely misclassifies the image. So trying to fool neural networks has become popular because it has been noted that they have certain blind spots, and by identifying those blind spot via a fool. So everybody is now trying to fool the networks. We can actually, once we know the blind spots, we can try to do something about the blind spots. So we can try to improve our networks so that they are not any more susceptible to such blind spots. So the idea of having an adversary is actually helpful in improving those neural networks. Finally, when we talk about generating text, what people mostly do in natural language processing is probably not so much using GANs, so these generative adversarial networks, but something called language modeling. Language modeling is just the task of predicting the next word given the history. So you try to predict the future given the history. That's also what your auto spell in your mobile phone, for example, is doing, right? You have a certain history, and the model suggests to you the next word to be generated. And when you have a language model, you can produce text. So you can also do this with your mobile phone. You just produce text, or you like with Google autocomplete. So this task has become very important on the one hand because now we are able to, those models have become very powerful. Now we are able to produce text written by a machine that actually looks like human written text, so which is a cool thing. And the other thing why language modeling is important is because it is a good pre-training task, for example, for BERT. And because in BERT, for example, as I told you, they have this masked language modeling where they mask out some words and then try to fill in the missing words. And if a model is able to do that, it really understands language. And therefore, this language modeling has been seen as an unsupervised or self-supervised task, which allows the models to infer natural language understanding. And so many people use this as a self-supervised task, which is cheap, so you don't have labeled data that you have to put a human to that's creating it, but you can just get it by yourself from the training data. And it really allows the models to understand language. Now here are some reasons why the language models have become so good. Because nowadays we have like transformer models. This is a better and faster model, so it can be parallelized, so therefore it can be trained on much more data and web scale. So we have better models and more data that they can be applied to. So the performance of these models, of these language models, have become better and better. And in previous time there was a website called Talk to Transformer, which you could go to, and then you could let the computer, you would give some prompt, like some initial words, and the model would complete those initial words to produce text, right? And and that's really cool, and you would see that it would work really well. I think nowadays the website has been taken down, but maybe there are similar such websites around where you can play around with this text generation ability. When we talk about an agenda for the next years, and that's what I want to conclude with, or almost conclude with, is certain aspects that people are working extensively on at the moment is to get introspection and explainable deep learning. So people often say that deep learning is black box. So it makes some decision, but you don't really know why it makes some decision. And that's really something that people want to overcome, because we want to know, why is this machine making this decision? Imagine you're applying for a credit and the bank is automatically scoring you and then just giving you an output, no, you do not get the credit. But you really want to have reasons, why is it not giving me the credit? Or imagine you're taking an exam and we feed this into a deep neural network and it says you have failed. But you would like to know, why have I failed? And this explanation is especially important also for the humanities, because humanities people are not satisfied typically with only having a classification. They also want to know whether this classification is reasonable. So therefore we ask the model, why is it making this classification? So we can maybe find out, okay, it's actually making something false by looking at the explanation it's giving. And on the other hand, it's just not enough to do classification. Reasoning and understanding the classification is very important to humanities people. Another aspect that's coming up is we want to have fair deep learning, no biases. Imagine you train your model on public data, and this public data encodes a lot of biases, such as gender biases or demographic biases against certain people from a society. Let's say the elderly people or foreigners, right? So if you apply such a model to your data and you classify, for example, you imagine a deep learning model taking an application of somebody who wants to apply for a company, and this person wants to apply, and then he's giving some information such as that he is Hispanic or whatever his cultural background is, let's say Hispanic. And now the model would have learned from Wikipedia, from Twitter, or wherever that like Hispanics is somehow negatively associated, and then the model would make the classification that this person should not get the job. So this is kind of unfair, right? Because we don't want to include all those biases that some humans may have on random humans may have on the internet into our machine learning models. So that's really unfair. So how can we enable fair deep learning without biases? Another thing is efficient deep learning. So our models are, especially BERT, they are very memory intense, and they also require high computing power. But that's not good for the environment, right? So that wastes a lot of resources. And with the general trend in society and all our environmental issues that are really facing us from year to year and get more severe from year to year, it's really important to develop efficient deep learning architectures. And the final thing is adequate evaluation is very important for the years to come. Why is that important? Because nowadays we have text generation models like in machine translation or in other text generation tasks such as summarization, which become really, really powerful and good. But the evaluation techniques that we have, uh, they they face this problem that if you generate text, that there are many, many different ways in which you can generate equivalent text. So if you want to say Peter was the best, or like Peter liked the burger, so there are really different, many, many different ways of saying this. Like Peter enjoyed the burger, Peter enjoyed it. It was the burger that Peter enjoyed. So they're like almost like for such a short sentence, maybe not an infinite number of possibilities. But if the sentence were a little longer, we would really have to deal with an infinite number of potentially generated text. And so our evaluation measures should really take this infinite of possibilities into account and should really be able to understand the meaning of text, right? So previous evaluation metrics that we had, they were just focusing on shallow lexical overlap. Does the generated text contain the word cat and the human reference? So usually when we have evaluation, we have a human reference against which we compare. Does it also contain the word cat? And that was maybe sufficient for those previous architectures, and for the more limited scope of text generation that we have. But nowadays we have really much, much better text generation models that are really able to paraphrase also. And therefore we also need much better and more adequate evaluation techniques. So this is what I think is the agenda for the next few years in deep learning for natural language processing. And I want to conclude with deep learning is rapidly advancing. Number of conference participants has also exploded. Like in the last few years, much money and many big players have come into the area and into the arena. And now human-like tasks such as generating text become addressed. Well, previously it was mostly like low-level tasks such as part of speech tagging or some classification tasks, but now also uh, computers um, computers have the potential and have the ability to really do tasks that previously we only addressed to humans. And also at the same time, we have also seen that there are still many limitations, like this fooling. So there's a real really big literature on fooling neural networks, like exposing their limitations. And one of those limitations is that they really adapt to low-level statistical cues still, and oftentimes cannot make. And with these low-level statistical cues, because they're also in the test data, they seem to perform very well on the test data. But then when we make feed in a different distribution, such as the ones given by adversarial examples, then we easily find that those models will fail, right? So while the models have really become much better, we've also seen that they still in many areas do not work in the same ways that humans work, and there's still a long path to go. And this is actually the last point that I want to make. So there's some hypotheses which you may have heard of, which goes back to the 1950s or so. I think to John von Neumann actually, like the inventor of the computers, who said that there's a singularity, and this singularity means there's such a high level of increase in intelligence, like computational intelligence, that it really generates a world that we cannot dream of at the moment. So it goes really up to a singular point, and it has been speculated. So there are several laws, like computer power is doubling every few years or so, and like at one point computers become as smart as mice, and then they become as smart as humans, and then they become double as smart as humans, etc., etc. So that would lead to the age of the singularity. And there's some people speculate that this may actually happen now, so that we are at the beginning of this process, because now we see the computers become much better, and this is possible. But and it's possible that it has maybe actually happened, but this is still, we're still in speculation here. It's also possible that this may still take 50, 100 years, or may never happen. So we'll see what will happen, and at the moment we don't have enough evidence to make very informed guesses.